All right, everyone. Welcome back to class. All right, so any good questions? How's the assignment going? Going good? Easy? Hard? You guys saw the announcement, right? So, yes. Actually, let me pull that out. Actually, I'm gonna go log into stuff. I'll show you guys. Canvas, dashboard. Let me type this on my own end and enter because I save. Because I gotta show everyone this, and yes, it's gonna be recorded. Click announcements, and let's drag that puppy right here. Oh, look at that, some announcements to make. Oh, I could create a new announcement if I wanted to. I was like, hello all, let's have a meeting today, Friday, October 1st. Then please bring any questions or concerns to the class. Here's your Zoom link. And then, yes, computer assignment 3 is based on 2, so if you did well on 2, hint, hint, 3 is kind of the same thing. You just plug in and change different numbers. But for those who are like time management or trying to figure out how to do these assignments on time, I would strongly suggest, and I underlined strongly and bolded it too, that if you haven't had the first half done by this Saturday, I'd start. So then you guys don't get caught up at the end. So just showing everyone on screen. I sent these announcements. I don't want someone saying, I didn't get any emails. I'm like, I've been sending a lot of material out. All right, so your question was about how do I start this assignment, right? And you're like, oh, how to put these states in. Let me pull out the assignment again. Oh, that's a Zoom. Actually, I'll just pull out the Zoom. CMOS stuff, that's my page right there. Here's the assignment, CA3. So let's look at it. Okay, yeah, it's literally the copy paste of, well, not copy paste, it's more like, okay, here you go, here's your system. For exercise 1 to 3, use the discrete system described by the difference equation, y of n. Let me just do this right here. Y of n, don't worry, I'm just copying, minus 2r cosine omega naught yn minus 1 plus r squared yn minus 2 is equal to r sine omega naught x of n minus 1. All right, now let me just pull this puppy here. So this is your linear time invariant system. So what do we do? Convolution, but I'll talk about that later. So what I want to discuss is why am I saying, oh, if you did 2 good, then how you're gonna do 3. So if you think about it, suppose, well, let's just put an A0 here, right? And then let's call this term A of 1, right? And then let's call this one A of 2, huh? I'm getting these numbers based on the delays. Like, here's a 1, here's a 1, here's a 2, here's a 2. You see that pattern? And then it's equal to r sine. This is a coefficient, by the way. It's right here. Oh, here's a delay, x n minus 1. You see that minus 1? What should I put here? B of? There you go. Where's B of 0? There you go. Simple, eh? And then for those who are like, no, I gotta follow procedure, here's your answer. Or not answer, but easier way of seeing it. A of 0, y of n, plus A of 1, y of n minus 1, plus A of 2, y of, can you see that color? Yeah, it's okay. N minus 2 is equal to B of 1, x of n minus 1. Simple. And then if you wanted to draw this block diagram, which I will show you now, let's do the easy one. Actually, which block diagram do you want?
Actually, wasn't that minus a sub 2?
Minus a sub 2? So what I'm doing here is I'm tucking the minus into a of 1 and this a of 2, well, the plus, it's already plus. So this right here, here's a0. Here's a of 1, and you see how I have a plus right here, but this right here is also a plus. I'm just tucking in the minus for our purpose's sake. And then you see that? That's our LTI system. LTI. There you go. That's the keyword for next week too. So now back to, okay. So for everyone in this room, which block diagram do you want?
Oh, do the transpose.
Transpose? All right, because you asked for it.
Can you really like identify the node?
No, it's all right.
The node. You know what I'm saying?
So let's, before we draw it, so what do you remember about TDF2? What do you remember about that? You remember that you have the feed forward path in the front, right? So that means we're going to be expecting B's in the front. And then at the end, we're going to have feed back paths. And then the cool thing about this is we have our input, which just goes straight into our feed forwards, and then our Y, which goes straight into our feed backs. Remember that? For a transpose direct form 2. So now, if we have B's on this side, we have A's on this side. How many B's do we have?
One.
Just one. And because someone probably has big OCPD, I'm going to draw it the way... Okay, let's just draw this node first. I'm going to put a B0 here. Okay? But you already know that B0 it's equal to 0, so it doesn't exist. But you do know we have a B1. There you go, huh? And yeah, that's it. So this is X of N. And now for the pesky delays. Actually, no, let's start the feedback path. We know that I'm going to plus this rate. Actually, there's nothing there. You can't plus anything there. Let's do this. Yeah, I'm just going to do a wire. Y of N. We do have, oh, where is it? 1, 2, wait, we have 2 delays. We have A0, A1, and A2. A0 is automatically this wire. A0 is a wire. So it doesn't do anything, it's just there. So we only have to draw 2 gain blocks, which means I'm going to do the following. A1, A2. Simple. Oh, got me there. I'm going to write that there. Minus. Don't forget your minuses. Put that minus in there. So the topology we're facing is we're tucking in the minuses into these coefficients. All the outputs on the left are all positive. They have plus signs. But when we solve for y, then they turn them into a minus symbol, which means we've got to put a minus in there. That made sense?
Yeah.
Sweet. Actually, let me put this off. So now back to our thing. How do we delay A2? Just go through delay. That's it.
How do we delay?
Then we're going to add this to this and this. So that means you got to have a plus. Okay? And then how do we delay this and this? There you go. You say getting this, but there's nothing here. You could put a summation node because you guys are engineers. You guys like procedures. But I'm going to be different. There you go. And then don't forget your error. It works. You could put a plus there, but we're not adding any inputs. We're just purely just adding a state.
Right.
All right? Actually, okay, someone has big OCPD. Where's my markers? Let's put that plus here. Plus, okay? So now you're asking about states. So the assignment I labeled here is asking for, okay, draw your block diagrams and generate your state equations for your direct form 2 and your transverse direct form 2. And that's a good reason to, well, we'll see in a bit. Let's see. So remember how I told you about how to do state space equations? So for all purposes' sake, I'm going to start on the bottom and I'm going to call this node Q of 2 of n plus 1. All right, we're about to implement the state space equations. And the reason why I started here and not here is, well, for surprise. What happens when Q2 goes through the delay block? Q of 2 of n. All right. Now let's pull out the other marker. Let's pull out the green. So now we're adding some value here, some value here, some value here to give us the next state, which is Q of 1 of n plus 1. Okay? Simple? So what happens when Q of 1 goes through the delay? Turns into of n. Yes, there you go. All right, and the reason why I put this plus sign there, but you don't have to, is because this is our output node. But what can you say if this really was a true node? So ideally, okay, if you remembered, y of n is equal to, should be b of 0, x of n, right? Plus q of 1 of n. However, we don't have a b0 term. It's just gone. Which means y of n is equal to q1 of n. So that's why I put this plus sign, because someone's probably thinking, hey, why do you have a q1 of n here and they're both the same signal on the same path? Yeah, I think someone would have asked about that. So does that make sense? Is that easy?
Yes, thank you.
And now the next question you asked was, where do I put these like states? Where do I put them? So the way I've been training everyone to code, and it's natural, so I gave some comments on some people's papers. They were not treating their states as an actual vector. They were treating them as just a variable, just a value with a variable with just one element inside it. They're not treating it as like some type of vector. It's okay, but then it's gonna hurt you in the long run, because then how do you store something in that node? So what I'm trying to say is, remember how I was saying, okay, here's our x input, and we had this Dirac delta, remember the Kronecker delta at 0, right? And then I told everyone, oh, you have to have this pre-length, okay? And if I were to draw this in memory, right, an array, how this position right here would be 0, and then this would be 0 right there, and then this right here would go down here, right? How I was telling everyone, okay, this right here, these two zeros, you generate them by doing zeros of 1 pre-length, right? The reason why I was trying to get you to do this, you can either do this or that, but this one's shorthanded, unless you get like a whole bunch of delays, is that you can replace them. So, okay, if no one understood what I was trying to say, let's try to put, okay, I'm gonna draw it right here. Here's our q of 1, right? Q of 1 of n. So you know here's our 0, right? And all the vectors we've done in this class are based on, well, this code right here, the zeros, 1 of pre-length, this right here, and then I'll put that, and then this would be like zeros of 1 end length, something like that, right? Remember that? I was trying to get everyone to do this type of topology, because then all it is just punching numbers in. So for q of 1, instead of doing the 0 stuff, here's q of 1. And what did I say for this assignment? Let me see. So for the transpose direct form stuff, q of 1, which is at the top, is just 0, just 0. So actually, here's 0, and n is equal to 0. Q of 1 is 0. So here's our 0, here's our 0, and then this position should be the 0 that corresponds to... Huh? Oh, oops, thanks. There we go. Actually, let me zoom that into... I'm trying to show someone this. Okay, so you know how we had our input, right? This right here is our n is equal to minus 2 right here. N is equal to minus 1. And then this right here is our n is equal to 0, right? Here's n is equal to minus 1. Or 2. N is equal to minus 1, right? N is equal to minus 0, right? I was doing this zeros pre-length, but I'm putting zeros here just so you can see it. And then this would be zeros from 1 to end length, right? So all you do is, if you know that here's your input, right, and you're treating the third element, this right here, as your n is equal to 0, then by looking at this vector, you look at here, that's your n is equal to 0, just punch in your values in there. But for our assignment, it's just 0, so that just stays there. However, okay, I'm gonna get a second page or a third page. Let's pull that guy out. However, for our Q2 Q2 state, remember we're doing, so I think originally it was zeros of 1 to the length of n, right? I think it was this, right? This is how you would instantiate your entire variable. And then you know how we had with our input, okay, I'll write this down here. Our x, I'm just gonna write this again. 0, 0, 1, zeros of 1 length, end length, right? This would generate all those zeros past n is equal to 1 down to 50, right? This would be n is equal to 0, right? And these two would be n is equal to minus 2, minus 1, right? Okay, so for Q of 2, following this topology with our input, we're going to have a 0 there. And then what's the assignment say? The assignment says we need to punch in at n is equal to 0 our sine of omega. So let me write that down. So n is equal to minus 2. Okay. As we're following the input. Here's our impulse response at n is equal to 0. Here's a 0. N is equal to minus 1. And now here's our n is equal to 0. What do we put in there? R. Because this is a coefficient, we can do the star sine omega naught. And then you can do zeros of 1 end length. And there you go. That's how you save your states into, well, your states. So whatever values into your states.
Is that exactly how we type it in MATLAB?
Yeah, if you want to, or you can just replace this with the pre-code stuff I did, which is zeros 1 to pre-length, and pre-length is equal to 2. Or 3 or whatever, however many delays are in the system. So you can either do this to visually feel it, or you can do this if you want to see more code. That made more sense. And then same thing with let me show you. Let's pull this out. So you see right here we have our Q of 1, and Q of 1 is n is equal to 0. Q2 same thing. And actually, it's this one here. This is the one I was thinking about, y of n. So the same thing we did with y of n. Let's see. We're looking at the arrays. So remember you have, let's do this. Let's do that. And here's n is equal to 0. All right. So what did I put? Let me pull that out. I should have the assignment on my hand. Okay, so we're looking at n is equal to minus 1 and n is equal to minus 2. So for my sake, actually, should I snipping tool that? Nah, I don't have to. All right, everyone just remember that for me. So we're going to look at n is equal to minus 1, and we saw that we have r sine of omega. And then this one was an r squared. Did I get it right? Yeah, let me see. Did I get that right? No, r minus 2. So it's minus r to the negative 2 sine of 2 omega naught. Oof, I forgot the omega naught. You're going to have to.
I just told him no. I said no, you didn't get it right.
N is equal to minus 2. There we go. So actually, let me just write it better here. This is messy. Minus r of minus 2
This makes a lot of sense.
sine of 2 omega naught. Here's this n is equal to minus 2. And then here is minus r sine omega naught, which is n is equal to minus 1. And then this is 0, because we have nothing at state 0, or y is equal to 0. So this right here is our oh, I didn't change the camera. There you go. It's much better. This right here is going to be our intro to our ZSR. which stands for zero, no, not ZSR, ZIR, zero input response. There we go. So what I mean by a zero input response, there we go, is, let me just draw this right here so you guys understand what's going on. I think Dr. Stubert, he's doing a kind of okay job, but I want to show you what it really means. Is, for example, let's say I have some system. Let's just draw some system, right? And let's say it has some capacitors and maybe an inductor and maybe a resistor too, right? Here's V in, here's V out, and a function of time. All right, so let's say I just stored something like maybe, I don't know, 1 volt here. Okay, and let's say this is 1 milliamp. Okay, if I were to give you some piece, and then I say, okay, just turn it on. Here's ground, and here's VDD, just connected to some switch. And I tell you, okay, while the input is 0, there's nothing in the there's nothing being, like, you're not kicking the box. We just want to see when we plug in our device, we just start powering it on. Let's see what it does. Let's see what it has. Okay, I'm about to turn on my circuit, and then once you turn this on, let me just short this. Once you turn this on, now whatever was here, here's 1 milliamp, here's 1 volt, and eventually this goes to 0 volt or 0 milliamps, and this also discharges. So then you'll see something like this. Here's 0, and then you just see this pulse. That right there is our response due to 0 input. We have nothing going into the input, and we're purely looking at the states of our system, which can be found by a ZIR. Okay, 0 input response. What is the response of the system with no input? There's no input to our system. We're looking at, oh, here we have some plus, we have a charge on a capacitor, we have current going through an inductor. What does our system do with memory? There's memory inside the system. Now the other block diagram, let's say I draw the same block. Here's a capacitor, and here's a resistor too. Here's V in, here's V out, and then let's say this is discharge, so it's 0 volts. This right here is 0 milliamps, so there's nothing in our system. But for a 0 state response, we're gonna kick our boxes. So what I'm trying to say is, suppose you're a running man and you just have this big boot and you just kick it. You just kick it really hard, just an impulse, which is a Dirac delta. You have this pulse and it goes to infinity, and then the delta, this width is probably approaches 0, really small width, really high amplitude. You just kick your box at t is equal to 0. What does your system do? So if you do kick it, oh, you'll have a lot of high frequencies, because capacitors, well, they like to take high frequencies. And this inductor, well, it doesn't like a lot of change. So you'll see some response. It'll probably be something too. The point is, what does your system do with when there's nothing in it and you just kick your box? You're just kicking your box or system. And this is basically known as a ZSR, 0 state response. Okay, so does that make any sense? So this is basically the practical way of seeing this. Like Dr. Stubert would say, oh, here is a system with some capacitor value. Here's Q1 with a value before n is equal to -1, n is equal to -2. Now figure out what it does. And in the end, there is a theory, and I'll tell you the surprise right now. This is going to generate some output, and this is the output due to the ZIR. It's going to give you some value. Let's just say, I don't know, something, A. And now, this right here is going to also give us an output due to the 0 state response, ZSR, okay? But what if I told you, what if instead you're lazy, instead of doing this and then doing this, a ZIR and a ZSR, why don't you just do them both at the same time? So by the power of superposition, you can just add this and add this. So looking at, let's say here's our ZIR, right? We're the same running person and we're kicking our box. We're looking at an impulse to a system that already has memory. That is called our total response. So if I were to summarize it, Y total response is equal to the 0 input response plus the 0 state response. And this will be your answer for a good majority of this next couple exams, I think 3 and 4. But I think for the purpose of the first exam, I think we're going to be looking towards kicking the box. We're going to be looking towards impulse responses, aka ZSR. So what is our system made of? What are the gains? What's in this thing? So with that introduction, this is page 4. Let me get to what I have for today. Let's see. So I did try to so before I go on, does everyone understand how to finish this first half of the assignment? You can draw these block diagrams, generate your difference equations, please, to like verify your work. And there are 3 unique sets. Just someone was saying, "Oh, I'm gonna copy the same one. Look, I did the assignment." I'm like, "Oh, you didn't finish the assignment. It's the same code 3 times." It's like, "But I did each figure." I'm like, "I'm not looking for figures. I'm looking for if you understood the assignment." So that's why I'm like grading heavily based on do you understand your stuff. And then here's the for loop, hint hint, same thing as computer assignment 2. And then now you know how to do this. And then what I say here is plot them and then compare them. And you see the system right here, right? It's going to be the same response. Actually, I'll tell you this right now. This right here, direct form 1, direct form 2, and transverse direct form 2, the states I put here, they should all be the same. Okay? So that's your verification. Compare this with exercise 2. Actually, let me see. Oh, that's exactly, okay, let me talk about that too. Actually, that's a great response. Oh, let me go back to it. Okay. Now, let me pull this puppy out. Boom. So to reiterate what I said, so exercise 2, you're developing a code, right? And all you're doing is just x is equal to, I don't know, zeros of 1 pre-length. And this right here is determined by the delays, number of delays. Okay? Then you have a 1 here. And then zeros of 1 and end length. So whatever your end of time is, so n is equal to 50. Okay? So this right here is just your, you already know this is your Kronecker delta. That's your Kronecker delta function. And all your systems, all your codes, the df1, df2, and then tdf2, all of them will take the same input. Okay? And then they will all give you some response. But you know that this, and this are the same system. So they better be the same. So it's like, oh, you're going to probably see something like this, or they should all be the same. Same output. Okay, that's our impulse response. We kick the box. So to draw that, I'm going to draw this. We're just, here's my shoe. We're just kicking each box. And you'll see the same response that comes out. Okay, who's chatting the message? How do we implement ZIR into code? ZIR into code. 0 input response. So that means it's the states. That's exactly what I discussed right here. let me see. Aha, here. See, this is how, so to implement the zero input response, this right here is our Kronecker delta, right? How do we make it a zero input? Just zero it, just put a zero in there, that's it. And then here's your states. Oh, Q2, Q1, simple. So this right here would be how to do this setup we have here, and this right here. This is just setting it up for the ZIR. We have zero input, and we're looking at purely the states. All right? Does that make sense? Answers your question? How to implement? Just make X. Oh, don't make it nothing. You have to have a vector in there, obviously. So point is, and here's one thing all the engineers like to do. They do the assignment, but they're not playing with the assignment. Actually, let's see. Actually, should I get to the code? No, I'll show you that code later. Here's my camera. But actually, before I talk about that, I'm about to talk about this. Where is that part? Exercise 2. Okay, back to this. So for exercise 2, all you're doing is a ZSR. You have nothing in your system. Okay, you have nothing in your system. So that means your Q's are equal to zeros, Q1, Q2, and your output is also equal to zeros. So there's nothing. All your Q's and all your Y's are initially at 0. You're just kicking your box. Here's your input. All right, but for exercise 3, you're implementing a IR. So this right here, you're gonna put a 0 right there. So same code, literally that. So you have 0, 0, 0, 0. You have nothing in your input. It's all just purely zeros. And now you just replace these values with whatever vectors you had. Q1 is equal to 0. Here's n is equal to 1. N is equal to -2. No, wait, 0, -1. And I don't know, maybe there's some value A, and here's your value B. You know what I mean, right? We're looking purely at these states because they have memory. They have memory in our system. So that's the whole point, the objective of the first half of the assignment. He doesn't tell you. He hopes you like understand what he means. But I'm here to tell you it's a ZIR and a ZSR. The second assignment, exercise 2 is a ZSR, and then exercise 3 is a zero input response. Here we kick our box. Here we, let me draw that. Here's DF1, DF2, TDF2, okay? Same input. But this input is just zeros. Just put zeros in there. There's nothing. And we just turn them on to VDD. Here's VDD. Here's VDD. What does it do? We just turn on our system. Boom. What states does it have? And then eventually you'll see, oh, it has some response. And these two, all these three should, I'll tell you the answer. They should all be the same. I think so. So does that clear up everyone's questions for the first half of the assignment? Yeah. If you practice the way I coded it from computer assignment 2, that's the reason why I was trying to train everyone that way. Because if you did it the way I told you, and for those who try to do the Q, didn't make Q a vector, yeah, you're going to see it here. You have to make Q a vector for this to work. All right? Easy? Sweet. Yeah? Filter function? Think so. Yes, actually, yes, you can. All you do is you already know your A's, you know your B's, put an impulse response. So what someone said in class, and that's actually a good question. How do I know if I'm right? And that's a good question. And actually, there's another, no, I'll talk about that too. So what he was saying was, okay, how do I verify my answers? And let me pull the coefficients I had. This was page 5. So remember this right here that we developed here. Here's our A0, A1, A2, B1, right? So you know that we have 2 delays, right? We have 3 of these values, right? That's how many delays we have. So if we have 2 delays, we're expecting 3 values, 3 numbers. So our A is going to equal A of 0, A of 1, A of 2, okay? But our B is also going to, because we only have one B, just shadow it. Here's B0, B1, B2. And you already know what these 2 values are, right? And all you got to do is Y is equal to filter B, A, and then just put your Dirac delta in there. And there you go. Is that it? And then you can verify your impulse response based on the filter function itself. You put an input in there and then see what it does. Make sense? Simple. And make sure this is a vector too. Someone's going to forget that. All right. So that's the first half of the assignment. So that one should be easy peasy for everyone to get done and then make my grading easy. And now let's look at the second half. And I did try to model a quiz based on it. I was trying to, okay, so convolution, that's the crazy dance he's trying to make you to do. He's like, okay, here's convolution. We have our y of n is equal to some b and then x n minus k. We're delaying it. And then he says, oh, to get the impulse response, I'll talk about that too. He's like, okay, here's our input, which he puts a Dirac delta, and then you get this b. So, okay, to translate what he has here, let me put that on the side. No, I'll remember that. Put that there. To translate what he's trying to tell you, because I remember going through this, and this was tough too, is your output is going to equal, let's just say from 0 to n of b of n is equal to 0, n is equal to n, b of n, x of n minus, actually let's call this one k, minus k, right?
Yes.
So let's say we make x of n is equal to the delta function, Kronecker delta, right? So what this basically means, when does this Kronecker delta turn on? So actually, okay, for this condition of n is equal to 0, when does it turn on? It just turns on at n is equal to 0. And now here's x of n minus 1, which is just equal to the Dirac function, n is equal to 1. When will this turn on? When n is equal to 1. All right? Now you see the pattern, right? And then it only turns on at this value and then turns off for everything else. So what I'm trying to say, let's just make this one equal to 3, is this is basically, here's b of 0, x of n minus 0, plus b of 1, x of n minus 1, plus b of 2, x of, actually I'm just going to make it, minus 2, plus b of 3, x of n minus 3. And you know that these are all delta functions. So that means, what's his name? Actually, is that how I want to explain it? This is a delta function, this is delta function, this is delta function, this is delta function. Just replace all these x's with x with that value. Is that how I want to tell you? Oh, that doesn't look right. Let me see. Because the point of these responses, I think that's how I was going to get it to you. B of n, y of n, h of n. Oh, no. He's talking about the actual value itself. Never mind. So if you're looking at purely h of... Oh my gosh. No worries. If we're looking at h of 1, so n is equal to 1, out of all these functions right here, so ignore these plus signs, which one's going to turn on? This one right here. Okay, this right here is going to be a delta function, d of 1 minus 0, which is equal to d of 1, which means this right here is 0. This right here is d of 1 minus 1, which is equal to d of 0, which is actually a 1, and then all these are off.
Right.
So that means at h of 1, you get whatever this is, b of 1. And then h of 2, which is equal to b of 2, and then so on. So that's what I was trying to explain with that part. So what I'm trying to tell you is, here's our gain value. Here's the gain value, b of 1, which comes from a feed forward block. Here's h of 1. And if I were to walk backwards, h at 0, the first point in our system, is going to be b of 0. H of 1, b of 1. All right? And then that is what I want to get everyone to for this next part of your assignment, which is, oh, now that you figured it out, this is the impulse response is the gains of your circuit, which I can show you right here. So for exercise 4 to 6, here's the system, right? So you know that I just told you that h of 0 is equal to b of 0. So that means what's your first gain block? B of 0, and then here's b of 1, right? So actually, here's h of 8. What is this gain block? B of 8. Makes sense, eh? And let me pull out the assignment. Or is it 8? Yes, there's 8. Okay, so if I were to do your assignment, and I do like doing your assignments. Is this 5? Hopefully this is 5. Okay, this is 5. This is 6. Let's pull out 7. There we go. Don't worry, we'll get to your quizzy too, but I might have to re-change one of the problems. This is 8. So what I'm trying to tell you is you have b of 0, b of 1, oh, b of 0, b of 1, up to b of 8, right? So how many gain blocks do you have? 8, right? How many gain blocks do you need to draw? 9. Because b of 0 counts as 1. B of 2, and I'll show you what I mean. So if you were to draw the, which one should I draw? DF1 or TDF2? So which one do you want me to draw? Direct form block diagram 1 or 2? Actually, no, I'm going to do direct form block 1.
Come on.
B0,
Easy way.
B1.
In the video last year, he said he thinks he can do the TDF2.
Who? David, don't let me find out.
It's a 20-minute video I watched.
B5, B6. Does it bother anyone if I do this?
We can't even say it.
Oh my gosh. Yeah, you gotta tell me about that. B7 and B of 8, right? Okay, you guys really wanted me to do that state? Or, okay. I'm too lazy. There you go. See, and then all you do is just delay your blocks. D, C. So here's a D, D, and then down. Oh, wait, I'm forgetting so many D's. Here's a delay, and here's a delay. Okay, and then here's a plus. Yep, it's all messy, I know. There we go.
You really speeded.
Yeah, because I don't want to waste time on this. There you go. You like that? It looks like a shoe. So that's how you would draw it. And then how do you implement this in code? Remember that stuff that we did in the second assignment and even in the third assignment? All you do is here's C of n, which is equal to, and should I get to the meat and cheese of this?
The meat, cheese, potatoes.
Because I want to show you this, but I also want to show you the cool trick, which is what we're going to try and implement in this class, the circ shift function. So convolution is basically, okay, here's y is equal to from minus infinity, or n is positive infinity to minus infinity of the impulse response h of k x of n minus k, right? And then I guess this right here can be n. So what we're doing here is, here's our h response, right? H of k, right? So h is 0, 1, 2, 3, 4, 5, right? But for this one right here, so this one is the same. So it doesn't change. It doesn't change at all. But this right here is a flip. Okay? So we're going to be flipping our input. And instead of the input, let's just say I drew a ramp function. So 0, 1, 2, 3, right? Instead of this right here, x of k, right? It's going to be flipped to be x of minus k. So everything just gets flipped on its axis. Here's 1, 2, 3. Okay? And the whole point of convolution, and if you had pieces of paper, is we're going to take this and we're going to multiply it to this actual block diagram. So what I'm trying to tell you is, I'm trying to figure out how to show you this without making it too complicated. And actually, okay, we have to. Page 9. Yeah, you guys are. So let's just say here's our impulse response. 1, 2, 3, 4, 5. Okay? And then here's h of okay, I'm gonna call it k. Oh, thank you. Let me just tap on that there. Right? You see that? Let me put that right there. And here's x of k. And I gave you an input of 0, 1, 2, 3, right? 1, 2, 3, 4. Okay? 1, 2, this is a 2, this is 3, this is 4, right? 1, 2, 3, 4. Okay? So the first thing in convolution when you're doing it in this digital format, and I'll pull out this other color, is we're going to flip this. So what I mean by flipping, actually, let me draw it right here closer. So here's our n is equal to 0. N is equal to 0. And I'm going to draw this backwards. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, there you go. See that? So this summation, okay, I'll write that right here. Y of n is equal to h summation from minus infinity to infinity of h of k x of n minus k, is we're going to look at n is equal to 0, okay? So n is equal to 0, y of 0 is going to equal, so we're going to look at this. I'm going to look at the first one. So what happens when at k is equal to 0 and n is equal to 0? So this right here, no, not that one. N is equal to 0. We're looking at n is equal to 0. That's not what I want to say it, actually. H is 0. And then this right here will be x of 0, okay? So the next thing I'm going to do is I'm going to go to, actually, k is equal to 0. K is equal to 1. So if k is equal to 1, here's h of 1. And since we're at n is equal to 0, this right here is x of minus 1. Does that make sense? Now I'm going to look at k is equal to minus 1 right here. I'm going to look right here. Plus, plus. So here's k of minus 1, right? I'm going to look at h of minus 1, right? And then here's our n is equal to 0. We're at times n equal to 0, right? This is 0. So we're looking at x of minus k. What's k? Minus 1. So minus 1 times, well, minus, right? It's just a 1. See that? Does that make sense? Yes or no? So what I'm trying to tell you is here, yeah, I'm trying to figure out the best way of showing it to you. So here's K, right? We're looking at K, okay? And here's H of -1, right? Here's H of 0, and here's H of 1. What I'm trying to tell you is we flip this, and now instead of X going forward, it's going backwards. So here's -1, here's 0, and here's 1. So it's going like backwards, if you know what I mean. Does that make more sense? Or actually, let me do this. So I'm gonna look at y is equal to n is equal to 1, right? So we're at n is equal to 1. So let's look at k is equal to -1, okay? So when k is equal to -1, what's this right here? H of -1, right? But now we have to look at this input. We have a -1 already there, but we're looking at k is equal to -1. So we have a -1 minus -1. So the minus turns into a plus. So it becomes -1 plus 1. X is equal to 0. Okay? Now, let's look at k is equal to 0. What do we have here? H of 0. Okay, we're looking at this. We're just sweeping k. We're looking at n as a constant value. We're just sweeping k. We're looking at the summation. Okay, so k is equal to 0. We have h of 0. All right, now we're going to have to look at x. Since n is 1, right? Actually, what did I do? N of 1. Okay, here's 1 minus -1. Oh, what am I doing? So this is a plus 1. This right here, okay,
I thought that was 2.
x of n is equal to 1. So we're going to put a 1 here. Here's our n minus -1. So that becomes a plus. This becomes a 2.
That's why I was like.
Oh, I'm so sorry.
I was like, whoa.
I got to show my work too.
No, you're
So
fine.
here's n is 1 and minus a 0. And what's that? Just 1. And then this right here is plus h of 1. And then here's x of 1 minus, here's k of equal 1, which is 0. There we go. So what I'm trying to say is, look at the pattern. This h right here that's not being flipped is just going forward in time. Whereas this one right here is kind of going backwards in a way. You see how I'm trying to tell you this? So we're taking this signal, we're flipping it, and then we're just going down the line. Yes?
Can you move the video sharing to the left side? Everything is covering some of the work there.
There you go. Easier? So I wanted to do it right here, but okay. So does that make sense? Does that make sense to everyone? We're taking this input, we're flipping it, and we're just here. This h is going forward in time with k, and then this x is going backwards. But the one thing they have in common is this. There's a point in common where, like, oh, here's h is 0. When time is equal to 0, n is equal to 0, you have h is 0 and x is 0. So then stuff goes, for the h's it goes forward here, for the x's it goes forward this way. So does that open everyone's mind into the world of convolution and the digital concept? Make sense? So now I'm about to do your quiz, which I tried to do, but I have to explain convolution first. Yeah? Oh. Oh, yes. I think it's in the back.
It's hard to get that.
Oh, here it is. Yeah, here you go. You can take a piece of paper right there. So, actually, yep. So if everyone wanted to see, we're actually gonna try and attempt this one. I tried doing this one, but my math kind of came out a little weird. But I'll try to explain what I was trying to do. But we're gonna try and do the digital sense. So, to re-exaggerate, let me just put this right here. 1, 2, 3, 4, 5. Okay. Here's our h of n. Here's our input. 0, 1, 2, 3, 4. Here's 1, 2, 3, 4. of n, right? The first thing we do is we flip this. So we're about to implement convolution. I'm going to draw this right under here. And I'm going to draw this right here. We're going to call this one our output. It's going to be big. There we go. So the first thing we got to do is we got to flip x of minus n. I'm going to call it minus n if that bothers anyone. So we flip this. So here's 0, here's 1, here's 2, here's dot, 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 right? So you know that we're going to multiply everything. So the way I'm going to teach everything is look at this signal right here. Here's n is equal to 0. And we're just going to place this on top of this signal. So this right here gets multiplied to, here's h of 0, x of 0. This point right here. So we're going to multiply this input to this impulse response, this h of 0. Okay, and I'm going to put a plus right here. H of minus 1, x of 1. Okay. So you know that here's our middle point, right? When we go backwards with h, we get a minus 1, but we go backwards here, we get this plus for 1, right? But you know that, well, there's nothing here. H of 1 doesn't exist, but we do have this. This is 0. Don't worry about that. Well, what I want to get to everyone is, actually, let's try this. Plus, we're going to go forward in time. H of 1, we're going to go forward. So we're looking at this point. However, we're going to have x of minus 1. But what's x of minus 1? Or is that what I want to show you?
Negative 1.
1. X of 1 minus 1. Is that how I want to show you? Because we're going to multiply these two, but there's nothing here. That I want to show you. X of 1, h of minus 1. No, that's not how I want to show you. Because what I'm trying to get to everyone is, you look at this signal, and then you look at this signal, and you just multiply on top. So this right here would multiply here. This would here would multiply there. And then you would add their summations. So what I was trying to get to, I'm trying to figure out what's, my brain's not working right now, is here we have a 0, and here we have a 1. 1 times 0 is 0. Here's a 1, here's a 0. This all should multiply to 0. So what I'm trying to tell everyone is this first point is going to be a 0. Okay? So the next signal I'm about to do, here's n is equal to 0. I'm going to shift this to the right. So now here we have our following signal. Okay, here's 1, and here's n is equal to 1. So if I were to do this signal, let me draw it like this. This point right here, here's n is equal to minus 1, and I'm about to multiply this to this. Okay? Actually, I should use a different marker. I want to see if I can show you this. So this right here is multiplied to this. And then this right here is multiplied to this. And then this right here is multiplied to a 0 and another 0 and another 0. So what I'm trying to tell you is this right here is a 0 multiplied to a 1, right? What do we get? We get 0.
0.
So that's 0. But here's a 1, and we're multiplying that to a 1. We're getting a 1, right? So I'm going to put a plus 1 there. And then every other number after that goes to 0. Okay? So the next value that we have here at n is equal to 1 is a 1. Okay? Make sense? Now, I really want to hammer this, because this is where stuff starts clicking. Okay. Is this page 10? I think so. Oh gosh. Page 10. That means this is page 11. Page 11. So here's our impulse response again. This is where stuff starts making sense. 1, 2, 3, 4, 5. And now I'm about to shift my signal again. So instead of it being here, I'm going to shift all this again to the right. Okay, here's our thing right here. Here's 1, here's 2. Here's this. 1, 2, 1, 2, 3, 4. 4, 3, 2, 1. Okay? So now this is where I start hammering stuff down. We're going to look at this X input. Here's our H, and we're just going to put this on top of this. So we're going to look at this, multiply these two together, and then add it to this right here. Multiply this together, add it to here. And then this right here is a 0, here's right here. And we're going to repeat this pattern until this input starts going inside this block. So what I'm trying to say is, here's a 1 times a 0, we get 0. Here's 1 times a 1, get a 1. Here's a 1 times a 2, we get a 2. And then this becomes 0, 0. So what is our value at n is equal to 2? We get 1 plus 2 is equal to 3. See the pattern? And then if you wanted to keep going, I'll show you this again. And this is how you would do it on your exam, by the way. Let's do it again. I'm going to shift the input again. 0, 1, 2, 3, 4. And then this is our x-axis, n is equal to 0. We're going to do the same pattern again. So this times this, this times this, this times this. And now you start seeing the pattern, right? So here's, I'm going to show everyone the answer. Here's 0 times 1 is 0. Here's 1 times 1 is 1. 2 times 1 is 2. And then you start seeing our signal up here too. And here's 0. You start seeing the pattern. What's this equal to? 6. This is when this stuff starts getting really messy. So this value here is going to be 6. Cool? And now let's get to our final point. All right. Oh, sorry. And this is the final point. And then you got to do this process again. So here's n is equal to 0. 4, 3, 2, 1. There we go. And now we finally shifted our signal all the way to the right. Here's n is equal to 4. Okay. So we're going to multiply this right here. Here's n is equal to 4 to n is equal to, is this n equal to 4? 1, 2, 3, 4. Here's 4, 3, 2, 1. No, wait, hold up. 4, 3 is equal to 1, 2, 1, 0. So actually no, this has to be multiplied to this, sorry. 0, 1, 2, 3, 4, 3. This right here gets multiplied to here. And this right here, this here gets multiplied to here. And then this right here gets multiplied to that. And you start seeing the pattern, right? So if here's 0 times 1, 0 plus 2 plus 3 plus 4. So now here's the pattern I'm trying to get to everyone. This right here looks like our signal, but backwards. Pretty cool, huh? Huh? Oh, there you go. This right here, look, here's our 1, here's our 2, here's our 3, and here's our 4. And then we, like, look, here's our, remember our input right here? Here's our backwards input. Here's our 0, 1, 2, 3, 4, right? You start seeing it here too, right? But the only difference is we're just now we're just adding our input. So what's this equal to, by the way? There you go. And then our final number, n is equal to 4, will be a 10. 10. And now you start seeing this cool pattern. So now what I want to get to everyone is, in reality, this signal is not a length of 5. It's actually a length of 4 because we're only focused more on this right here is data and this right here is data. So this right here is a length of 4. So there's only 4 data points. And we're multiplying these 4 data points into a unit step that has 5 data points. So what I'm trying to tell you is, page 12, and how we're doing on time, 6:43 or 6:41, 12, is, I'm going to draw this in the analog state. Here's our unit step, 1, 2, 2, right? And here's our analog signal that's coming in. And let's just draw it like this. Here's this triangle over here. Here's our X input, right? We start shifting this inside the triangle, right? And we're starting to see like, oh, we're finally in here, right? But then we get to the point where this triangle, this signal, is finally in here. So what does this mean for you, everyone? So you just realize that, okay, we're adding these points and we get this number. In other words, the area of whatever our signal is. The area, it's an integration of our actual signals. Now here's our triangle, which is an area of, I guess, 10 in our sense. And I'm gonna call this one time 1. So now we start moving it down here. There we go. And then you notice, well, here's gonna be, I'm gonna draw this for my own sake, 1 and 2. So you're gonna see this pattern. So it slowly starts, the input signal, which is being reversed, slowly creeps into our unit step. So you're gonna see some slow creeping in up to whatever our area is, which is 10, I'm gonna call it. And then you're gonna get the area of whatever our triangle is for, okay, it's gonna sweep in here for 1 second. And then now that our triangle starts to leave, let me just use the green marker. Our triangle starts leaving the system. And then, well, for this signal, it just slowly starts leaving like this. So that's what I'm trying to show you. So this right here is kind of the solution to the first half of the quiz. I tried to mathematically get it for you, but I messed up the math, I guess. But if you wanted to practice this with actual signals, it's easier to see this if you put a line up there. So in other words, if you were to use squares, so here's our H response, right? And here's our X response, right? And we're just using, here's 1 and 2, here's 1 and 1, right? You're literally putting this square into here. Actually, this might be easier to explain. Here's X of minus t, right? Starts at the beginning of time. Here's Y. So at the beginning you see no area, there's nothing in there. But then let's say the this rectangle is right here in the middle. No, that's a bad triangle. Actually, it starts at 1 right here in the middle. Here's 1. So we have this square that goes into the middle. So what will be our value, right? Here's 1. Here's 2. Our value here is gonna slowly do this. Here's 1. So you see what I'm trying to say? Okay, point is, once our square is finally here, it's already moved 1 second. So why we're at 1 second? What's our value after our square moves for 1 second? So here's our actual square. It's inside this. What's the area of the square? 1 times 1? 1. But now the square moves for another second. Now it's here. Here's our new square. What's the area of the square after another second? 1. And then the square leaves the box again. And then we start seeing this decrease. See? Pretty cool, huh? So the point is, we're just taking shapes and we're just adding their areas together. It's like a weird form of integration. Does that make sense? So what I was trying to get to you guys for this next portion of the assignment, your job is to, well, let me show you what like how to verify this in MATLAB. So I created this code right here. Actually, let me put this right there. Actually, is that it? No, this is the assignment right there, but where is that other thing? There it is. So I was trying to represent this in the time domain, but no, it didn't work. But let me show you what I have here. Is this it? Let me show you. Here's our input. No. Ah, here it is. Sorry. So this is Q quiz 5 part or question 2. Okay, so what I did was, okay, we have n is equal to 0 to 20, and I didn't check my chat thingy. Here's our impulse response, right? Just put ones. Here's our x, and I just set this little code. Here's our pre-length. This is what I called our pre-length. Here's our n is equal to 0. Here's 1, 2, 3, 4. And then I just developed some type of signal, right? Actually, okay, if anyone wanted to see it. Figure 500, right? Oh yeah, by the way, you can actually type your assignment right here too. So 500. Stem, actually, okay. Let me run this. Clear variables and run this. F9. Oh, hopefully that didn't end the video. Oh, did I press F9? Okay, cool. Stem and X. Oh. X. That's because, did I make it a 10? I think I made it a 10. F9. And let's run the same code again. X must be the same. N is equal to 0. Did I make it 15? We need 4 more numbers. There we go. There we go. That's what I wanted to show everyone. So you see how it looks like, oh, we're slowly getting up there, and then we have this thing right there, and it starts going down. Let's check our answer. Where is it? Aha! Here it is. What do we have at time is equal to 0? 0, right? Here's our 1. What do we have there? 1. And that right there is a 3. That right there is a 6. And then that right there is a 10. Is that what we get in our little solutions right here? Look at that. 1, 3, 6, and 10. And then if you keep going down, that's how you verify your answer. And then someone's asking me, hey, David, how do I do assignment 3, the second half? Cough, cough.
Yeah.
So you want me to explain this? So all you're doing is you flip your signal. Flip your input, right? We're flipping our input. Okay, because someone's probably asking this. Oh, okay, you know, screw it. Watch this. See? Here's our input, right?
Mm-hmm.
And now let me flip it. Okay. Your job is, here's our signal. Here's our original signal, but I didn't put the time axis there. And now we flip it. And all you're doing is you're just multiplying this flipped signal, and I'm looking at the first end. So actually, let me show you what this code right here means, because someone's probably asking, hey David, how do I implement this in code? So if you wanted to see this, why did I do x of 1 end to minus 1 of end minus, I guess, 8, which is the number of delays right there, right? So why did I start at the end? So if you just did this, x of 1 end, this is going to give you the final point, which is our final flipped signal. So we've always been using this final point. So here's our array right here, right? Here's n is equal to, here's position 1, here's position 2, here's position n. This final point is the end point. So we're looking at the end point, and we want that to be the first point in our signal. So we're taking this, and we're kind of putting it back into its original format. So the point is, we start with the last point, then we go down a little bit up to however long our h response is, which is end minus 8, which is 8 delays. So that's how you would finish this assignment. So this right here is for the direct form 1. So if anyone want to know how to implement that using a matrix. So instead of doing this, so someone's probably going to do this, and yes, it's annoying. Not for me, but for you. Why is equal to h of 0 dot times x of 0. And then you would continue this pattern, h of 1 dot times x of 1. Oh wait, no, not that. Plus. And you see how this can get annoying up to 8, and then you're going to have 8 lines of code? Instead of having 8 lines of code, why don't you just implement this? There you go. Pretty simple. So what we're doing is, here's our signal or impulse response. It's the normal signal times our flipped input. And we're just starting with the last one. And then, oh, there's one thing I got to talk to you about. And that's this little thing right there. You see that dot and that apostrophe? That's how do you transpose a signal. So here's our flipped signal. I'm going to run this right here. Don't worry, about to end. F9. And we have this vector. What happens when you do vector multiplication with two vectors that are the same size like that? It's not going to work. So the only way for this to work is you flip this like this. So you put this this dot and this apostrophe to get this tall vector right there. So in a nutshell, and this is the last thing I'm going to talk about, page 13, long, is y is equal to h, which can be, I guess, let me just do for an example, h0, h1, h2, right? Times x0, x1, x2, right? Just for a small example. Here's h times x. And you know that when you do multiplication between a 1 by d, I'm going to call d as a delay, and delay by 1, what's the result? A 1 times 1 matrix. So that means what I'm trying to say is it's basically this plus this times this plus, okay, h of 0, x of 0, plus h of 1, x of 1, and then dot, dot, dot. Does that make sense? This times this, and then add it to this. So instead of 8 lines of code, you have just 2. So that right there should get you going with the assignment. If you understand how to do it, then it should be pretty easy. And then you know how to change inputs, right? Really simple. Any other questions? And then I guess everyone's going to have to do a transpose direct form 2 for homework, eh? Using the same theory. You just flip your thing, throw it into your system, use multiplication. So if there's any questions, let me know. Any other questions? No, we're good? All right then, everyone. Have a good night, and see you next week.